So today's lecture is about the derivatives of inverse functions. So I have a little picture here, okay? And so we're going to say um, just for like speaking ways, a lot of times books will call f inverse of x g of x, okay? So this is my original function f, and this is its inverse g, okay? Now we can tell this that they look like they're inverses of each other because all inverses should look like a reflection across the line y equals x, okay? Now I want to point out that this point here that they have in common, so that's not exactly the same point, but they have, if f of x has AB on it, then g of x has the point BA, okay? So that means if f of x, or if f of a is equal to b, if g is its inverse, then of course we know that g of b would be equal to a, okay? So I'm going to just kind of eyeball the tangent lines in here, okay? Say that looks like about tangent there. We'll say here's one here, okay? So I'm going to just sort of draw in the slope of this tangent line here, right? So here, and then let's see, how do I want to draw this one? I think I want to draw it this way. Oh, that's a terrible drawing. Okay, let me draw this out so it looks a little bit more, okay. Essentially what I'm trying to show you, except my drawing is off, is that this is, if this were like P and this were Q of my slope, then the slope of G, or actually it would be the derivative, F or G prime of B would be, let's see, it would be rise over run, so it would be P over Q, okay? I don't know what these heights are, right? And then these, really, I practiced this a couple times and it failed epically, but this one would be then, this is Q, no, that's the same. This is P and this is Q. So the F prime of A would be Q over P because that's rise over run. So essentially the derivatives of inverses at sort of the opposite, right? The coordinate is different, but they have them in common, right? They're part of the same point. They're reciprocals of each other, okay? So kind of I have a little baby proof here. So this is called the inverse function theorem. And we're going to let f be a function that's both invertible, which just means it's one-to-one and we're allowed to find its inverse, and differentiable. Means we can find the derivative everywhere. That means it's nice, smooth, not broken. And so we're going to let y equals g of x be the inverse of f, right? So that's the way we write it, but I get tired of saying f inverse, so I just prefer, we'll just call g the inverse. And so we do know that we have this rule by composition that says that f composed with g of x, right? If two functions are inverses of each other, when I compose them in either direction, I get this, right? This would also be true. Now I'm just going to choose this one over here, and we're going to do the derivative of it, okay? So we're going to do the derivative of both sides with respect to x. And so this side over here, if I do the derivative, I'm going to do, this is my Leibniz notation, right? The derivative with respect to x. Then on this side, this is literally the definition of the chain rule here. So that would be f prime of g of x times g prime of x equals, and then the derivative of x is just 1. So I want to figure out what the derivative of g prime is, right? The derivative of the inverse. So if I divide by this piece here, f prime of g of x, then we end up with 1 over f prime of g of x. And so that means that g prime of x is equal to 1 over f prime of g. Okay? So let's use that for just a moment, okay? So we have that our g prime, or our g, I'm sorry, is the cube root of x, and we're going to find g prime using the inverse theorem, which means g prime of x is equal to 1 over f prime of g of x, okay? Now, this is not a difficult one, but this is the inverse, so that means if we wanted to figure out what f is really just x cubed, okay? So using this formula means I'm going to take f prime, so I need f prime of x, and that would be 3x squared, right? And then this says then put g in it. So then I have f prime of g. So I already know that g is this, so I'll have 3 and then cube root of x squared. I'll put the 2 under there, okay? So if I simplify this, this is really 3x to the, I'm going to change it to power over root, a rational exponent, so this would be to the, let's see, 2/3 power. Okay, so that's my f of g of x, is 3x to the 2/3 power. So that's my f prime of g of x. And so then that means that g prime of x is really 1 over 3x to the 2/3 power. All right, you might be asking yourself, like, why did we go through all of that when I could have just done, okay, well, g is really x to the 1/3, and so that g prime of x is really 1/3 x to the negative 2/3, which really could be written as this, right? You're right. That was a much simpler thing, okay? But that is really not the bonus of this theorem. I just wanted to show you that it actually worked. But the real reason that we really like to know this theorem is because, I mean, in this case, it was easy to find f, right? Or sometimes it's really easy if we have f to find g, the inverse. But sometimes that's not possible. Sometimes g is really hard to find. It's really like algebraically complicated to find what g is physically, but we could still find the derivative at a specific point. So let's actually use it the way it's meant to be used, okay? Because that's really kind of overkill to do something that's simple. Okay, so like for instance here, we have f is x to the 7th plus x plus 1, and we want to find g prime of 3 specifically. In this case, we really can't find g prime of x because if I try to do that, right, let me just attempt it for a second. I get x equals y to the 7th plus y plus 1, and then I could do x minus 1 equals y to the 7th plus y, but how am I going to solve for y here? Like, it's very, I'm not even sure what's the next step to find my inverse here, okay? I might have to complete the square somehow or do something crazy, but it's really challenging, okay? So what we're going to do instead is use our inverse formula. Now the important thing to remember is that g prime of 3, right, is attached to the same thing. So if that would mean that where g prime, actually let me just leave off the prime, where g of 3 is something, we know that f of something equals 3, okay? So in this particular case, so here's the thing. So I'm going to set this equal to 3. I get x to the 7th plus x plus 1. Now sometimes it's not so algebraically complicated that we can't do this with algebra. Like we could actually do 2 equals x to the 7th plus x. But then after that, I'm like, I'm going to just have to kind of fly, just try out numbers. If this is the case, then these have to be kind of simple, like something that I can sort of look at and go, oh, well, if x was 1, I would get 2 here. Now, sometimes it would be algebraically simple enough that maybe I could find it using algebra, but in this case, not so much. So I should be able to, like, if it looks algebraically complicated, like start thinking, what if I put in 0? What if I put in 1? What if I put in -1? Or something maybe a little bit more obvious, okay? So just eyeballing this, right, I can kind of see that if x were 1, then I would get out, really, in this case, if I put it up here, if I put in 1, I would get out the right answer, right? So that means that f of 1 is 3. So that means that g of 3 is equal to 1, okay? So if we use this, okay, let me write out our formula. So we know that g prime of 3 is really equal to 1 over f prime of g of 3, okay? So we don't know what g is, right? But we do know what g of 3 is. It's actually 1. So really, g prime of 3 is really just 1 over f prime of 1, okay? So see, this is how we can actually use it and where it makes sense, is that we can't actually find g, but we can actually figure out what g prime of a specific number is. In this case, it would be 1 over f prime of 1, which we can find, right? Now, I kind of assumed some stuff here. So this is an x to the 7th, so it should be completely like positive, so it should pass the horizontal line test. And just as a quick check, I can say that f prime of x, actually I'm going to do f prime right now, so let's not write it under there. So f prime of x would be 7x to the 6 plus 1, which will, if you can kind of tell, this is x to the 6, which will always be positive. So I'm going to have 7 times something that's always positive plus 1. So f prime will always be positive. What that means about original f is that means that the slope is always positive, meaning f prime is, or f is always increasing. So it should be a one-to-one function that has an inverse, okay? And it's a polynomial, so we kind of know that it should be invertible. Or we should know that it does in fact have an inverse, okay? Okay, so if I have g prime, I actually can figure this out now. G prime of 3 is really 1 over f prime of 1. I know how f prime of x. I can figure out what f prime of 1 is. So I get 7 times 1 plus 1, which is 8. So g prime of 3 is really 1 over 8. Right? So I figured out what g prime of 3 was without being able to find what g is, right? But I can still find the derivative of the inverse at that point. Okay? All right, so we have another one. So you have f of x equals x plus e to the x, and we want to find g prime of 1. Okay? So the first thing that I always want to do, and of course we're assuming that g is the inverse of f, the first thing that I always want to do is I know that if g of 1 is equal to something, that means that f of something is equal to 1. So let's see what happens when I set f equal to 1. 1 equals x plus e to the x. Now in this case, I don't think it's going to be 1, right? Because if I plug in 1, then I get 1 plus e, which is that doesn't help me. It's not equal to 1. But I notice, right, anything to the 0 power is 1, and if I plug in x as 0, I'll get 0. So 0 plus 1 then would be 0. So that means that f of 0 equals 1. So that means that, oops, I don't know what I wrote here. G of 1 is actually equal to 0 then. Okay? So if g of 1 is 0 and f prime, or f of 0 is 1, then I know that g prime of 1 is equal to 1 over f prime of g of x, but g of 1 is 0. So that means I have g prime of 1 is equal to f prime of 0. Okay, so let's find g prime, or I'm sorry, let's find f prime we'll find g prime by finding f prime first. So f prime of x means I'm going to have the derivative of x as 1, and I know that the derivative of e to the x is e to the x. So I have basically 1 plus e to the x. So if I plug in 0, f prime of 0 is 1 plus e to the 0. E to the 0 is 1, so I get 1 plus 1. And so g prime of 1 is equal to 1 over 2. And that is my answer. So this is how it's useful. Okay, we can't find the inverse, right? Again, if I switch x and y, I would get x equals y plus e to the y, and that's not an easy algebraic thing to solve for y. So, but we can find the derivative of the inverse at specific points, though, if we can figure out the other coordinate. Okay, so again with these, right, they should either be algebraically simple or they should be something that like you can look at and think, okay, I can figure this out on my own without actually being able to have some project of algebra. All right, and so this is how we can use our inverse function theorem. We're going to take this and apply it to a bunch of trigonometric functions and figure out what their inverse function derivatives look like next.